Hi, my name is Callie Chappelle, and thank you for tuning into this video about the right-hand rule. This video is made for Physics 235 at the University of Michigan, but hopefully it'll be helpful for you no matter what kind of physics you are learning. So the right-hand rule is something that's pretty interestingly transcends a lot of different classes. It's something that you learn to utilize in Orgo. It's something that you learn to utilize very heavily in this class, which is focused on electricity and magnetism. So one thing that I thought was really confusing about this class is you are thrown in a very short amount of time a bunch of different right-hand rules, and it's never really explicitly told to you when you use each of the right-hand rules. So I wanted to go through the three big ones that we've learned thus far in the class to clarify when to use each one. So when do you use the right-hand rule generally? Well, you utilize the right-hand rule when you want to determine the direction of complicated vectors. Okay, so you use any right-hand rule, no matter which one, to determine direction of a vector. Okay, so we're going to be doing lots of cross products, especially in this video, and when you want to figure out the cross product to figure out the direction of the resultant vector, you want to use the right-hand rule because it's a lot easier than using unit vectors. Before we get started, I think it will help out kind of connecting what we know about unit vectors to how do we utilize these various right-hand rules, especially in the first context when we're doing cross products. So let's look at unit vectors. Okay, unit vectors. So we have three unit vectors that we use in this course, and these are pretty standardized, so that account for three directions. So I'm going to draw an axis here. Okay, and we have, actually I'm going to draw a straight line here, that might help out a little bit. So we have this, okay, this is going to be the y-axis. Oops. No, let me do that again. So if here we have the y-axis, and then here we have the x-axis, okay, and then in this, a slightly different color, I'm going to do, oh, nope, I wanted that to go back to the lighter color. Okay, and in a slightly different color, now in this purple, I think I'm going to do the z-axis, so you can tell that's kind of coming out of the page here. Okay, cool. So, here we go. Let's label this. Here we go. Okay, so here, this is the y-axis. This is the x-axis, and then here in this purple, this is the z-axis. So you can imagine if x and y are in the plane of the paper, this z-axis is coming straight out at you. So if you were doing this in Orgo notation, just let me know if you don't know what this is talking about. It would be written like this, where this z-axis is coming out of the board at you, this x is in the plane of the paper, this y is in the plane of the paper, and then this is the negative z-axis. If you're familiar with this, if we're using stereochemistry, use it. It's something that I like to use to conceptualize this because I learned Orgo before I did unit vectors. But if it's confusing you, just ignore it. Okay. So then we have three unit vectors that correspond with this. Oh, it's a little bit challenging to see. Let me do this in a little easier color. Okay. So this just has a magnitude of 1, and the unit vector that corresponds with the x direction is I hat. Okay, the unit vector that corresponds with the y direction is j hat, and the unit vector that corresponds with the z direction is k hat. Let me grab a color for that. Is k hat. So when we talk about unit vectors, just so you can understand a little bit better how I'm orienting my hands, I just wanted to go over this really quickly. So now that we are all on the same page with that, let's do the normal, what I'm going to call the normal right-hand rule. And there's actually a couple of variations, I know, to make this even more confusing, of the normal right-hand rule. There's one where you utilize your pointer finger, but the one that I'm going to teach that I was taught in this class, that I think is pretty common, is instead of using your pointer finger, we just curl our fingers in the direction of the cross product, okay? So if you're listening to this and you're like, wait a minute, I was taught this different way, that's totally valid. Both ways can be used and you'll get the same result, but make sure that you know one and stick with it. I'm going to be doing one where you curve your fingers in the right direction. Also, if you're watching this video and you're from Europe, apparently Europeans often learn it instead of the right hand rule, learn the left hand rule and do a bunch of other things. Well, I just combined do and utilize to doodleize. Well, don't doodleize it in this video because that'll make things really confusing. So if you are European and utilize the left hand rule, turn this video off right now. Oh, one other thing I just realized about unit vectors, if you want to figure out if we're adding unit vectors, I like to utilize this handy little triangle where it goes I, J, K, and then the arrows go like this. And then I like to remind myself that if they go in the direction of the arrows, it's positive. So if you do the cross product of I cross J, then you get a positive K. If you did if you did J cross I, you would be going the opposite direction of these arrows, so you'd get a negative K. If you did J cross K, you'd get a positive I. If you did I cross K, you're going in the wrong direction to these arrows, so you'd get a negative J. So this is a super easy way to add vectors. But let's go back to the normal right-hand rule. So the first question you need to ask yourself is when to use it. So when do you use this normal right-hand rule? Because each of these three right-hand rules we're going to go through, the normal right-hand rule, the thumb straight curve rule, and the finger straight curve rule, which are all variations of the right-hand rule, are used in different contexts. So you use this, the normal right-hand rule, with any at all cross product. And when do you use the cross product? You use the cross product when you have a resultant vector that is perpendicular to the two previous vectors. So if you had, x and y, if you're trying to figure out the cross product of x cross y, well, it's going to be perpendicular to both of them, so it's going to be in the z direction. And then if you're using unit vectors, you would, if you wanted to do x, oops, I know, I hate to use that cross, that's a cross, y. Okay, then we know x is in the I direction, we know y is in the positive j direction, so I cross j is a positive k or z, and we know that because you can see it here. Okay, so that's conceptually what we're doing with the cross product. Okay, and we have a bunch of cross products that we're using when we're talking about things like magnetic fields and dipole moments. And the reason why this is helpful is because we can use this to figure out the resultant direction, not magnitude, but direction of any vector that's utilizing a cross product. So how do we use this is the next question, okay? So now we know when to use it, how to use it. So let's say, I'm just going to write a general case, and then we're going to look at a couple of examples of particular equations in which we'd use this. So let's say that we need to figure out some cross product A equals B cross C. And just to get an idea of how this is going to be oriented, let's say that B is I hat in the I hat direction, or has the direction of the I hat unit vector, and C is J hat, okay? And we want to figure out the direction of A. We want to figure out the direction of A. So A, I'm going to write down here what you're going to be doing with your hand. So A is going to be represented by the direction that your thumb points, okay? B is going to be represented by the direction where you initially point fingers. And I'm going to draw a picture of this just in case, because you probably can't visualize this right now. Where you initially point fingers, and then C is going to be the direction that you curl fingers. Okay, so direction you curl fingers. Okay, so a couple of big disclaimers when you're doing the right hand rule. The first thing is don't use your left hand. I know that sounds really obvious, like of course it's called the right hand rule, I'm not going to use my left hand, but I have to do this all the time. Keep that left hand behind you. Don't use it. I know it's really tempting because you're writing with your right hand and you're like, I just want to do this with my left hand. Not going to work. You're going to get the wrong answer every time. The second thing you need to know is the order of the cross product matters. So B cross C is not the same thing as C cross B. So you need to make sure that you're doing this in the right order every time. Otherwise, you're going to get a sign error. And trust me, it's easy to do if you use your left hand and or you get this in the wrong direction, okay? So let's visualize what this cross product actually means. So first, we're going to do this. We're going to start here, because remember, we're going to go in order. So first, we're going to do B, and then we're going to cross C, okay? So the first thing that we want to do is initially point our fingers in the direction of B. And I already defined the direction of B to be in the I hat direction, which is in the positive X direction. So if I'm going to draw what my hand is doing, the first thing that I'm going to do, or I'm going to initially point my fingers in the direction of B, is I'm going to point my fingers in the negative X, in the positive X direction. So we know that positive X is this way. So if I was drawing a picture of what I'm going to do with my hands right here, I'm going to have my hands do something like this. Okay, so here's my hand, and we're going to point my fingers in the B direction, okay? So B is this way. The second thing we're going to do is we're going to point okay, so just so you know, my hand is oriented upwards like this, so my palm is here. So I'm just going to draw a picture of my palm. It would look something like that, right? Okay, so the second thing I'm going to do with my fingers pointing in the positive X direction as defined by B, the second thing we're going to do is curl our fingers in the direction of C, and we've already defined C to be in the positive J direction. We know that the positive J direction is Y, so this is up, so this is X, so I'm just going to write I hat here. And then here's Y, and we know this is in the J hat direction. Okay, so what are we going to do? Well, we took our hands and we're going to curl our fingers up like this. Okay, so if I was going to draw that, it would look something like this. Okay, pardon my bad hand drawing here. Somewhat challenging. Okay, but there's a thumb here. If your thumb is like this, and here's your palm. We started out where B was pointing this direction, okay, and then we curled our fingers up like this to be pointing straight up in the direction of C, okay? And you'll see that my thumb is pointing out, okay? So this thumb represents A, like we said up here, that A points in the thumb, and this is pointing out, okay? So B is pointing, okay, and outward is the Z direction. So B is pointing in the X direction, C is pointing in the Y direction, and out is pointing in the Z direction, and we know that Z is the same thing as K, so that is in the positive K hat unit vector. So it would be represented by the positive K hat unit vector. And we already figured this out, right? So when we did the cross product here, when we did I cross J, well, you get positive K, and that's corroborated by using our right hand. So if you don't want to go through and figure out the unit vectors every single time, just pull out your right hand, and you can do it super easily by just tilting your fingers around. So now that we know how to use the right hand rule, when do we use the right hand rule? So like the next thing that we want to do is look at some example equations. And I actually kind of want to make sure that you can still see this here. I just want to make sure you can see this, how to use it. So as we go through this, so let's see, example equations. And I just want to make a short disclaimer. So this video is geared towards topic material in this class before induction. So we may go over cross products after this, but this video is specifically geared towards when you'd use it for the topics of the biot-savart law, for Ampere's law, for introduction to magnetism, and talking about torques and dipole moments. Okay, so please note that. So here are some example equations. So the first time that you'd use this is when you are trying to figure out the magnetic force. Okay, so this is by far the most common time when you are going to use the normal right-hand rule. And you'll notice that all of these that we're going to talk about have some kind of cross product in it. So the relevant equations is when you want to figure out the force due to a magnetic field, you use QV cross B, or alternatively, you can use the other definition, or the other equation for finding the force due to a magnetic field, which is IL cross B, okay? And we're going to talk more in other videos about how to use these equations, where they come from, and what they mean. But essentially, this equation is used when you are asked about charge carriers. Charge carriers, so that's like electrons or like, like electrons or current in an external that means magnetic field, not force, B field. And then this is used generally when you have a magnetic field, when you have, I'll just uniform this, when you have a B field, and you also have plus a wire with current, okay? The second thing that you're going to use this for is if you are asked about torque. When you're asked about torque, and that's just the direction in which a loop of wire will turn on its axis. Okay, and the torque equation, you'll notice, is yet another cross product. So torque, which we represent using tau, the Greek letter tau, mu, so that represents the dipole moment. We're going to talk about that in a second. Cross B. Okay, and just so you know, this mu is gonna come from the finger, what I like to call this finger straight curve rule. And don't worry, we're gonna talk about that in a second. And this is usually given, or you might have to use the right hand rule backwards to figure it out. So if you're given the force and you're given the velocity, you can use the right hand rule kind of backwards to figure out what the magnetic field is. So what you do if you were doing this backwards is you know where your thumb's going, you know where your fingers start, what direction do you have to curl your fingers to get your thumb to go in this correct orientation. So that's how you'd use this backwards to figure out the direction of B, but more given the direction of B being the magnetic field. However, more frequently, this is just given to you in the problem. Okay, and the last thing, and this is a little bit of an esoteric example, in theory, you probably won't be doing cross products because there's a much easier way to do this without the cross product, but that's the biot-savart law. Okay, cool, that's how you spell that, and that equation is this. It's dB equals mu naught, and mu naught, that represents the permeability of free space, okay, over 4 pi times I, and then here's the cross product. I knew you were waiting for it, ds cross r hat over r squared. But we actually never end up using the normal right-hand rule for this. We always use not derivation, but a different version of the right-hand rule for this, called what I like to call the thumb straight curve rule. So I just wanted to go over these cases, so when you see these equations, you'll be familiar with when to use the normal right-hand rule and how to use it in those cases. So now the next kind is what I was just talking about here with the biot-savart law, and what I'm going to call the thumb straight curve rule. Okay, so thumb straight curve rule. And why do I call it this? It's not because I'm some crazy person who likes to come up with really long names for things. It's because this thumb represents what we know. So we're going to orient our thumb with the information that's given to us in the problem. So what we know. And then straight comes from the fact that we put our thumb straight, and then we're going to curve our fingers around our thumb to figure out the direction of the B field, okay? So when do you use this? This is when we are trying to figure out the B field, so the direction of the magnetic field created from a current in and this is really important, a straight wire. So we're going to talk about the thumb straight curve rule and then what I call the finger straight curve rule. Now this is by no means a technical terminology. I just like to think about it in my mind so I can keep the two straight about when to use them. So we use the thumb straight curve rule when we're dealing with current through a straight wire. When we talk about the finger straight curve rule, that's going to be for a dipole moment
or the direction of the dipole moment in a curved wire or a loop of wire with current flowing through it. But before we get there, let's talk about the thumb straight curve rule. We're going to use this when we're trying to figure out the direction of a magnetic field around a straight wire with current. So here is a fact for you. So fact, magnetic fields make circles around current elements, okay? So if we have a wire, so here is a really terribly drawn wire, and we have current flowing through this wire in this direction. Well, if I wanted to visualize what the magnetic field looks like around this wire, it looks like a bunch of circles around it, okay? It looks like a bunch of circles around it, and if here this is the end, it makes a nice uniform, or what should be uniform circle around here, okay? And it's going to be going in a closed loop, okay? So this is what the magnetic field looks like around a wire. And another important thing is this magnetic field actually drops off as you get further and further away from the wire. So here, really close to the wire, well, this is going to be a strong B field. But here, far away from the wire, this is going to be a weak B field, okay? So close, that makes sense. With close to the wire carrying a current, it's going to be a strong magnetic field, but way far away from where that wire is going to be a weak magnetic field. And that's exactly what we saw with the electric field as well. When you're close to a point charge, the electric field is strong, but as you go further and further away, it degrades. As the quote-unquote radius gets larger, the strength of the electric field goes down. So this is a fact about how a magnetic field is created by current moving through a wire. So that's what the biot-savart law says. So one thing that you may remember when we talked about the biot-savart law up here is that it makes a cross product. So you're probably wondering, well, Callie, if it's using a cross product, why are we using this silly curved rule? Why do we need to, if we're always going to be figuring out something that's a cross product, so things that are at 90-degree angles, how in the world does this actually end up creating circles in the way that I can actually curve my fingers around a current of wire and figure out the direction of the magnetic field? Well, it's actually pretty cool because when we use cross products, they actually naturally make circles. And you're probably wondering, as I was wondering earlier this week, how could that be? Okay, well, here's a really terrible circle, but if we have something at the middle of the circle and we have some radius r, well, the direction that is perpendicular to r will always be tangent to this circle, okay? So if you always have something that's tangent to this circle, as we go around the circle, it actually creates a circle itself, okay? It creates a circle itself, and if this is the magnetic field, right, it creates a bunch of vectors that when they're summed together, or when, like, in total, they actually end up making a circle, which is why, if this is the wire, so let's say the wire is coming out of the, it's coming out of the page at us. Yeah, funny little pause because I was actually doing the thumb straight curve rule with my hand to make sure that I was getting the orientation of the wire. So if the wire is here, so if we're seeing this head on, so if this is my eyeball and I'm looking at this straight on, and I'm seeing this, I'm seeing the current come straight out of the page at us, and I'm seeing the magnetic field creating this circle around it, okay? And this is what we're seeing right here. So this is how we utilize the biot-savart law. So remember, here's that law right here, and it has this cross product. Well, if I wanted to figure out the cross product every single time from this using ds cross r, well, I'm going to be doing this for a very long time because this is ds cross r, and then this is not quite right actually, because the magnetic field is like going in the circle, right? Well, it's going to take me a really long time because I'm going to have to do this for multiple places around the circle. It's much easier to actually use this nifty little trick to figure out the direction of B from this cross product right here by curving my fingers around the imaginary wire. So now you understand why this is so necessary, because I don't want to waste my time doing a bunch of this crap. I want to actually do it real quick while I'm struggling tonight with speaking. So let's talk about how to use this bad boy. How to use. Okay, so what we're going to do is the quick and dirty is we're going to point our thumb in the direction of current, okay? So thumb is going to equal current. And then we're going to curl fingers. So fingers curl. This results in fingers curl in direction of the magnetic field, or the B field. Okay, so let's do a quick example. So if I have a wire right here, and current is flowing through this wire straight up, what is the direction of the magnetic field? So what I'm going to do is I'm going to orient my thumb. The first thing I'm going to do is orient my thumb in the direction of the current. Okay, so here my thumb is, here's my fingernail, so you can kind of see where I am. Wow, this is a really terrible thumb. Okay, so I'm going to direct my thumb straight up, okay, in the direction of current, and then I'm going to curl my fingers around. Remember, I'm using my right hand. Okay, I'm going to curl my fingers around like this. Okay. Curl my fingers around just like that to get the direction of the B field. So you can see here, the B field is going to, let me maybe do this in a different color so you can see it a little bit better. So here is the B field going like this, B field. Okay, so it's going around this wire like this, okay? So you can see how I'm drawing the B field in a relationship to how my hand is curling, okay? So let's figure out what would happen. How would we do this if we were looking at this wire top down again, okay? So we're looking at the wire top down. You can see the current is coming out of the board at us. So utilizing our nifty shorthand here. So remember, this, a circle with a dot inside, means coming out of the board at you. And over here, maybe I'll draw, if you see this, that means going into the board. Why does it look like this? Because it's supposed to represent an arrow flying away from you. So if you have an arrow, okay, and you're looking at it this way, well, if it was flying away from you, you just see the feathers, which is this. But if you were looking at an arrow getting shot straight at you, hopefully that's not what's happening, you'd see something like this, which represents the tip of the arrow. So here, if we're looking at this current head on, well, I would stick, how would I do the curved hand rule? Well, I would stick my thumb out of the board straight at me, and I would curl my fingers around my thumb. So I curl my fingers around like this. Okay, this is gonna be really terrible drawing. Okay, and then I would have something like this. Wow, that was really poor. So the current is coming out of the board, and then my fingers are curling around like this. So that means that current would be flowing, I'm sorry, not current, that the magnetic field here would be rotating counterclockwise, okay, around this. So that's how you utilize the thumb straight curve rule. Again, it's called the thumb straight curve rule because I'm putting my thumb in the direction of what I know, which is the current, and it's the straight curve rule because I'm curving, my thumb is straight, and I'm curling my fingers to figure out the direction of the magnetic field, okay? So, looking forward really quickly before I move on. So why would we need to figure out the direction of the B field along a wire that has current going through it? Well, usually we're going to utilize this B that we know, this B vector that we know, and put it in other things, like to figure out the force due to the magnetic field, or to figure out the torque, okay? And these are going to be stuck into these equations right up here. So do you see how all of these equations, well, these three equations all have some kind of B vector, usually this is not going to be given to you. You're going to need to figure that out from other things. So it's important for you to know how to find that by using the thumb straight curve rule, so then I can utilize that direction to then plug into this cross product that we use the regular right hand rule for. So do you see why it's important to master when you use either of these cases? It's important because you're actually using one right hand rule to then utilize a different right hand rule for the next step. Okay, so let's do the very last example here or the last type of right hand rule, and I'm calling this one the finger straight curve curve rule. Okay, so just like the nomenclature is the exact same for the previous one, it's just called the finger straight curve rule because what we know is the direction of the current, which is what will be represented by our fingers, and it's called the straight curve rule because we're going to be curving our fingers, and our thumb will represent, my thumb, which will be straight, will represent the dipole moment. Okay, so this represents the dipole moment. And the little acronym, not really acronym, but the symbol for dipole moment is the mu with a vector arrow over top. So when do you use this? So when to use? You use this when you know the direction of current around a loop of wire. Okay, so this is when we have a loop of wire. So this is different. The finger straight curve rule is different than the thumb straight curve rule because we use the thumb straight curve rule when we have a straight wire, and use the finger straight curve rule when you have a loop of wire. And this is going to make sense because we used our thumb up here to represent the straight part, and here now we're going to use our fingers to represent the curved part. In both cases, what we know is the direction of the current, which is why we use our thumb here and our fingers here. But the difference is here the current is going in a straight line, which is why we're using our thumb, and here the current is going in a loop, which is why we use our fingers to represent it. So a good question here is, what is a dipole? What is a dipole? And honestly, that is a pretty good question because it's not very obvious that a loop of current has a dipole somewhat similar to an electric dipole. You're like, well, that's weird. If I put a positive charge and negative charge together, it creates a dipole. That's like somewhat intuitive, but it's like if I create a loop of current and that somehow has a dipole, just like a bar magnet would, that's not outwardly apparent. So one thing that we do know, though, is a quality of a current loop, which you can kind of think like somewhat non-intuitively, but a loop of current actually is kind of equivalent to a bar magnet. I'm actually going to draw this bar magnet a little bit differently. Is somewhat equivalent to a bar magnet in that on one side of the loop of current you have a north side, and on the other side of the loop of current you have a south side. Let me just make sure that I'm doing this right. Yep, yeah, okay. Yep, yeah, I just want to make sure that I do this the correct orientation. And on a bar magnet, you also have a north and south side. So you're probably wondering what this means. Well, if I had a loop of current, let's say that I had this like this, and it was oriented kind of parallel to you, then it would have a north side. So on one side of the loop would be north, and on one side of the loop would be south. We know that the north side, let me make sure that I'm going to say this right quickly. I really don't want to mess this up and have you be forever ruined because that's no fun. Yeah, so the north pole of a bar magnet is like a source, so we have arrows coming out of it, and then on the south side is like a sink, so we have arrows coming into it. Just like on a bar magnet, you have arrows coming out of the north side into the south side like this. The same thing happens with a loop of current. So a dipole is if you have a current loop, or if you have a bar magnet, and it's in a magnetic field, it will orient itself to line up with the magnetic field. It will orient itself to line up with the magnetic field, okay? And we're going to talk about this more when we talk about dipoles in a second. But what I do want you to understand is kind of the basis of where this is coming from and when you'd use this, and then how to use it as well. So we know that we'd like to know mu. So why do we even care about figuring out the dipole moment? Well, that helps us determine torque. It helps us determine torque because we know that torque equals mu cross B. Okay, and this is a cross product, remember, so we're going to use the regular right-hand rule for this, but we're going to use this by using the finger straight curved rule, and then this we also could actually use the thumb straight curved rule, or we could use something else, it could be given, and then we'll use the regular right-hand rule after we've done other right-hand rules to figure out the individual components, we'll use the big normal right-hand rule to figure out what the torque is. Okay, so that's where we're going. We know what a dipole is. We know, another important thing is the direction of the dipole moment, which you can represent using an arrow. I like to use kind of a big arrow instead of these little arrows to represent the dipole moment. This points in the direction of north. It originates from the north side of a loop. Okay, so here, if we have a dipole like this, the dipole moment would be this direction, and that is north, the north side, and that's what I'm saying here. That's a really terrible N. That's what it should look like. Okay, so how do you use this? How to use. Okay, so we know when to use, how to use. It's really easy. You're going to curl fingers in direction of current, and then in this case your thumb, so what we know is our fingers, we know current, we know how we're going to orient our fingers. Thumb points in direction. God, I sound like Dave Wynn. Okay, so Dave Wynn's is at least my instructor for this class, and he says things like direction and 0, and I find myself also saying those things, so please bear with me if I turn into a apparently 45-year-old man that has very particular pronunciation, then you'll know why that happened. So thumb points in direction of the magnetic dipole, or the dipole moment of a magnet, okay? So let's do this. So let's say that we have, remember we use this in cases where we have a loop of current. So let's say that we have a loop of current that looks like this, okay? So this is just like a wire, and we're somehow magically inducing a current, or a current is flowing in here. And I'm just going to do this so we can have a little bit perspective of what we're drawing over here. So first, let's do a top view. So this is my eyeball, and I'm looking down at it. I'm going to redraw this loop of current like this. Oops. I'm going to do it in red, I think. I'm going to redraw this loop of current just like this. So this is if we were looking down on it, this is what we'd see. And let's say that we have current flowing this direction, okay? So it is flowing counterclockwise around this current, or against this loop, this wire loop. So how would I do this? Well, I'm going to curl my fingers in the direction of current. So we're going to curl our fingers this way, okay, this way. So if I wanted to draw a hand, I know my hand drawings have like gotten worse and worse over the course of this video. Okay, so if I wanted to draw a hand with what this looks like, it would look something like this. And then my thumb, so I'm curling my right hand, my finger's that way. My thumb is coming out of the page straight at us, okay? So it's coming out of the page straight at us. And remember, this represents the curve of our direction, the curl of our fingers represents the current, and this represents the dipole moment. So this is straight out, or if you want to go fancy, in the positive k-hat unit vector direction. So this is out. Okay? So there's what our hand would look like here. So let's say, instead of looking at this straight down, let's say we look at this on the side. And this is one thing that I found a little bit confusing. So we're looking at it like this. So essentially, when we look at this, we're looking at it on the side, all we're going to see is a flat thing. Because, so if you were thinking about it, this is actually going off into the distance. in this direction, right, it's like actually going like this, but all we see is a flat thing. And let me get rid of that. Wow, okay, this is taking me a long time to erase. Okay, so we just see this, and then here this part's coming out at us, and this is going back into the board. So I feel like we're actually kind of seeing it, not really here, but like perhaps from like this direction, where this is coming out at us and this is going away. But anyway, we're seeing this is our loop, and again, our current is flowing down this way. Okay, so how would we orient our hands here? Well, this is a little bit confusing. Well, what we're going to do is our first, because this is pointing out, and our fingers are curling in the direction of the current. They're going to push, our fingers are going to come out of the board at us, and then they're going to go into the board, back into the board. And we're going to be using our right hand, because I totally just tried to explain it using my left hand, and then I'm like, he's not going in the right direction. So how would I draw that? Well, here the fingers are coming out of the board at us, and then curling back in. Okay, so it's coming kind of like that. Okay, so they're coming out of the board, and then they're going back into the board. Okay, and then out of the board, back into the board. And then what happens is after we curl our fingers around like that, then we see our thumb is pointing this direction. Okay, so here we go. I starts coming out at us and then goes back in. Okay, so there's I. And then we see that we have mu pointing in this direction to the right, also known as the positive I hat direction, like the I hat vector, okay? So one thing that you'll notice, these two things are actually the same, just in different orientations, and those different orientations correspond with the different ways that we're actually viewing the exact same loop with the exact same current, just looking at it in different ways, okay? The last thing that we should note is what happens if you have a circular loop, because this is all fine and dandy if we're looking at a rectangle, but what happens if we have a circular loop of current? We have a circular loop of current, okay? So let's say that we have this circular loop of current, and we're looking at this loop of current straight down. That's a really terrible loop I drew there, okay? So we have this circular loop of current, and we have the current is flowing this direction, and I want to know what is the dipole moment right here in the middle of the circle, okay? And we'll figure out why this happens in a little bit, but it's going to point in one direction. Now, one thing that you should know, actually I probably should have said this a little bit earlier, is how a dipole moment is actually defined. So dipole moment is defined as n, which is the number of turns in a coil. So if you have a coil and you have 3 loops in here, n would equal 4 here because there are 4 turns in the coil, n times I, which is the current flowing through this coil, or if in this case, if we've been looking at just one loop, so this would equal n would equal 1 here in one loop. Here, the current flowing through the loop of wire, or the coil, and then times something called the area vector. So this is the direction of the quote-unquote area. Now, what you're probably wondering is, you're like, hang on, Callie, if I have a circle, well, the area could be pointing up, but it also could be pointing down. How do we do that? Well, physicists, because they're really cool and like to make stuff up, no, just kidding, physicists would never make stuff up. Well, they kind of arbitrarily define the area vector, okay? And the area vector is going to be the same direction as the dipole moment. So I've actually kind of been lying to you. I've been saying we're using our thumb to figure out the dipole moment. Well, that's not entirely right. We're actually using our thumb to figure out the area vector, which just happens to be the same direction as the dipole moment. So, sorry for that quick diversion, but what reminded me about that is when we have a circular loop of current, the dipole moment in the middle is the same as the dipole moment of the entire loop of current. What I mean by that is the area vector of the entire loop of current is the same direction as the dipole moment, and that is the same everywhere in the circle, okay? So we're wondering, what is the dipole moment right there in the middle? So what we're going to do is we're going to, again, curl our fingers in the direction of the current, okay? So here's, wow, my claw hand here. Okay, I'm curling my fingers in the direction of the current, and I find that my thumb is coming. My thumb, if I'm curling my fingers in the direction of the current, is actually going back into the board. So you can't really see my thumb very well right there, but if it's kind of behind these fingers, and this is going into board. Okay, so that means that mu is going into the board, or aka in the negative k hat direction. Okay, maybe let me redraw this a little bit better. Let me try to. It's really hard to try to draw something while it's really hard to draw your right hand while you are simultaneously using your right hand to do the right hand rule. I was not predicting this to be nearly so artistically challenging. I actually am an artist. I know you're probably like, you're not believing me right now because I'm doing such a poor job drawing my hands, but it's true. Kind of somewhat sadly that I'm struggling with this so much. And then let me see. Okay, that's a little bit better. So we have our hands curling here, our fingers here curling in the direction of the current, and you can see a little bit better how this is actually, mu is actually pointing in the negative k hat direction, okay? So the last thing that I wanted to say is how we use this looking forward. So like I said, we end up using this, actually no, I'm sorry, one more thing that I wanted to say about this. The direction of mu in the case of a circular loop of current is the same direction as the magnetic field at all points, okay? So here, let's see, if we have this loop of current again, and we know that current is flowing in this direction, let's figure out the direction of the magnetic field at various points along this loop, okay? And we're going to utilize, remember, to figure out the direction of the magnetic field when we have a straight wire. Well, actually, in this case, it's not a straight wire, but we can pretend like it's a straight wire at each of these points, where I here is pointing in this direction, where I here is pointing in this direction, where I here is pointing in this direction, and I there is pointing straight up. The direction of the magnetic field. Well, remember, we use the thumb straight curve rule to do this, okay? So we're going to put our thumb, so let's do this one at the top first. We're going to put our thumb in the direction of the current, okay? So that's going to be in the positive x direction, okay? And then we're going to curl our fingers in the direction, we're going to see which way our fingers curl, okay? And our fingers curl this way, straight up and over. So if I wanted to draw a picture of what the magnetic field looks like at this point, I would draw something that's like this. Well, let's do the same thing here, okay? So here our thumb is pointing down, okay? Our thumb is pointing down. Our thumb is going to be pointing down. Okay, so let's draw the thumb pointing down because that's representing the current. And then, this is also a little bit challenging, but it's actually going to be like my knuckles are like here, and then my fingers are actually curled in like this. So if I was drawing the other side of my hand and my hand was see-through, my fingers would be curling like that, but I don't want to do that because my hand, in fact, is not see-through. So if I was drawing this, this would be going like this, and the direction of the magnetic field would be like that. Also, if you might want to go through and do this yourself to verify to yourself if this is the case, but here the magnetic field is going to go like this, and here the magnetic field is going like this. So what you'll notice here at the middle, at every point the magnetic field is actually going back into the board, and this is supported by what we figured out about this, that if I did the finger straight curve rule and curved my fingers in the direction of the current, then my thumb would point in the direction of mu. And what did I just say? Well, mu is in the same direction as the magnetic field of the loop, so that makes sense that all of these magnetic fields are going to be pointing in. The B fields are going to be pointing in, and that's the same as mu, which also points in, okay? So that's a really important thing to remember in looking forward. What equations do we need to know dipole moment for? We need to figure when we were figuring out torque. Remember, that's mu cross B. And then also if we wanted to figure out the potential energy, but that's a little bit less important, that is in fact negative mu dot B, okay? And in both cases we need to know the direction of mu, which we can figure out utilizing the finger straight curve rule. So this video is actually quite a bit longer than I was expecting, but hopefully it was helpful for you to clarify how to use all of these different right-hand rules and in what cases you do to do so. So hopefully we'll see you in later videos, and I hope this was helpful for you.